Hi everyone, I am Nicolas. I am working at MPIA as part of the Planet Genesis group with my advisor Paola Pinilla. And today I will show you our observations of substructures in disks around very low mass stars. So very quickly, this is the outline of my presentation. I will talk about planet formation in very low mass stars. Then I will show you our observations. We will discuss our results. And finally, I will summarize all the results that we got. So let's start from the beginning. Let's talk about planets. And nowadays, we know from missions like Kepler and other planet surveys that planets are almost everywhere. And we also know that most of the stars in Milky Way are M dwarfs, which means that probably most of the planetary systems are hosted by M dwarfs. And up to now, we have detected some complex planetary systems like TRAPPIST-1. And we also have detected giant planets around M dwarfs like GJ 3512. But these detections are hard to understand under the scope of our current planet formation theories, because we know that radial drift is, well, at least we expect radial drift to be very efficient in disks around very low mass stars and brown dwarfs. So here I'm showing a simulation of a disk around a brown dwarf, and you can see that by 1.5 megayears, the disk is already less than 2 AU in millimeter size. And this is in the absence of dust traps. So if we wanted to maintain the dust at longer distances from the star for longer timescales, we need some dust traps to keep the dust in there. And these dust traps would then also generate substructures in the dust continuum emission. We have detected some substructures in dust continuum emission. We have some cavities in SIDA1. We also have cavities in 2 disks from Lupus. But most of the observations of disks around very low mass stars look like the disks that I have here on the right. So most of them are observations with low sensitivity at low or moderate angular resolution. So these datasets are not deep enough for us to see the substructures if there is any in there. So we have the next questions. We don't exactly know how common are the substructures in very low mass stars. And also, we have found some giant planets orbiting M dwarfs. So can we find any evidence of giant planet formation around them? And finally, is there any evidence of this very efficient radial drift that we expect? To answer those questions, we observed 5 disks with high angular resolution ALMA band 7, so it's millimeter emission. And on top of that, we also added to our sample archival data of SIDA1, because SIDA1 is in the same star-forming region, Taurus, than our other 5 sources. So we have 6 very low mass stars observed at high angular resolution in the Taurus star-forming region. All of the sources were observed for about 30 to 60 minutes. So let's see our observations. These are the images that we got for the dust continuum emission of each one of the sources. And you can see that the dust continuum emission is pretty compact. I'm plotting the Neptune orbit for scale. So you see that 3 of them are more compact than the Neptune orbit, and then 3 are a bit more extended. Very nicely, you see we detected all of them. And we also resolve the emission in all of them in the visibilities. So that's very good because we can measure the dust continuum extent by analyzing the visibilities of each one of the sources. So let's take a look to the gas emission that we got. These are the gas emission of 12 and 13 CO for the compact sources, so the one that were in the lower row. And you see that particularly SIDA7 is very compact in dust continuum emission and is very much more extended in gas emission. And it has this strange asymmetry, arm, spiral arc. We're not able to describe what is going on in there, but it's much more extended than the dust. Then in JO420 and JO415, you can see very clearly that the cloud contamination is very strong. Actually, we completely lose one side of the 12 CO emission that then we recover in the 13 CO. And we recover the rotation pattern in all of the lines except for the 13 CO in this source, because the sensitivity is not good enough. Then if we look at the gas in the disks that are more extended, you can see that the cloud contamination is still an issue, except for MH06, where the gas detection is very good in both the 12 CO and the 13 CO. And since the detection is so good and we have detection in all of the velocity channels, we tried to model the Keplerian pattern around the star. To do this, we use the eddy package, but the problem is that even the best models that we got, they still leave these strongly structured residuals. We tried many different approaches. We tried different combinations of pre-parameters, fixing the geometry with different values, and nothing worked. The problem here is probably that there is a very strong correlation between the mass of the star, the inclination, and the vertical structure that we're unable to disentangle. So we need higher angular resolution and more sensitive observations to really understand or to really describe the rotation around the central star. But at least we know that it is more or less around 0.2 solar masses. So let's take a look to the substructures that we found. And again, we have these 6 disks. There are 3 that are a bit more extended, so we can directly detect substructures in them. And then we have 3 that are more compact. Since they are all comparable to their sizes are comparable to the beam size, to really describe the emission in them, we need to go to the visibilities. So these are the visibility modeling for the disks that are very compact. We just described them with a single Gaussian. And you see that a single Gaussian is a very good model for CDA7 and GO415. There are some 5 peak sigma residuals in JO420, but most of the emission is still very well described by a single Gaussian in this source. The peak in here in the original image is over 300 in signal to noise. So having 5 sigma peaks is still significant in terms of residuals. So there is something in there that we are not describing with the Gaussian. But the overall emission is very well described by the single Gaussian that we got. And then the sources that are more extended, you can see that CEDA1 is very well described by a single Gaussian ring. In the case of MH06, the same as GO420, so we have some residuals. The residuals are not significant compared to the overall emission, but they are still in there. So there is an asymmetry that we are not describing, but most of the emission is very well described by the broken Gaussian that we got. And finally, in JO433, we have the first tentative detection of a multi-ring system around a very low mass star. So these are the images for the continuum, and these are the images of the models that we got. We are going to analyze the dust continuum from the models, because we know that the models describe very well most of the emission in all of the sample. So let's talk about planet formation in our sample. We can talk about planet formation in the disk where we detected substructures, and we will try to see what do we need to generate these structures that we're observing. To calculate the dust mass, we just assume that the temperature is constant in all of the disk, equal to 20 K. And for the gas mass, we just go for 100:1 gas to dust ratio. So let's start from the first disk, which is MH06. We considered all the different processes that could create a cavity, but we find that the 3 of them are not really likely. You can go to the paper to see more detail about that discussion. So if we consider that there is a single planet embedded in there that is carving this cavity, we find that that planet would be like Saturn, a little bit less than Saturn in mass. For CEDA1, our substructure is very similar to the one that was already described in Pinilla et al. 2018. So we don't change the results from there. We also need a Saturn mass planet. And for JO433, we find that a planet that is like a third of Saturn or 3 times Neptune could explain the gap that we're observing. So very important in here is that from the observations that we got, we find that the substructures are consistent with giant planet formation. It doesn't mean that there is a giant planet in there, because we are just assuming too many things. So we need higher angular resolution and proper hydro modeling to really get better constraints. But at least giant planet formation is still allowed from our observations. If we take a look to the radial drift that we wanted to investigate, you can see that 4 of our sources have a ratio between the radius of the gas and the radius of the dust, which is close to 4 or above 4. Actually, for CEDA7, the ratio is about 6, and it's well over 5. So what we find is that based on the results of Trapman et al. 2019 and 2020, what he finds is that if the ratio is over 4 between the radius of the gas and the radius of the dust, then it is really hard to explain this ratio without invoking radial drift. So what it means is that we are finding here evidence that radial drift is at play and is very efficient in the disks, or at least we find that a result for the disks where the gas is well detected, because the other two that you can see that are just over 2 are the two disks where the gas is just poorly detected. There are for JO420 and JO415. So just to summarize all the results that we got, we find that substructures are directly detected in 50% of our sample, which are the most extended very low mass stars disks that we got. This doesn't mean that only half of the disks have substructures. It's just that in the other half where we didn't detect directly the substructures, we don't have enough angular resolution to see what is going on in there. So we predict that there must be something in there that is trapping the dust, but we're unable to see it. We need higher angular resolution data. The substructures that we did find do not exclude giant planet formation, which is a very good result. And finally, the ratio between the radius of the gas and the radius of the dust is telling us that radial drift is being at play and it's efficient in the disks that we are observing. So thank you very much.